Okay, so this will be a shortish podcast. We're going to talk about continuing on what we were talking about just last time I saw you. I'm on the top of page 10, and we were talking about, before we got to Mendeleev, we were talking about electrons, Schrodinger, Heisenberg, and how they were trying to predict and talk about, there's Panda, she didn't like this, talking about where those electrons are. So let's kind of talk about the periodic table. Mendeleev is credited for organizing the periodic table. He found a pattern, and we call that the periodic law, and said that when the elements are arranged in order of increasing mass, there is a property. Okay, we have since known that they've adjusted it. Now it's by atomic number, the number of protons, not the mass. And I think there's only like 4 places where mass and atomic number do not both increase, that the atomic number increases and the mass does not. Maybe if you get bored, you can see if you can find those 4 places. But otherwise, Mendeleev put them in and we saw patterns. And the elements they put in the same group, hence that's how we got the alkali group, alkaline earths, halogens, noble gases. But the cool thing was he actually predicted elements not yet that were not in existence, but he knew something that someday somebody should find them. So beryllium and iodine were examples. Some other examples actually were gallium and germanium. And so this is just kind of for informational look at the difference. He predicted its mass would be about 68. Okay, we know its mass is 69.72. Again, not too bad. Low melting point, it is a low melting point, about 80, 85 degrees Fahrenheit. Gallium will melt in your hand. Okay, look at the density, spot on. He knew its formula would be some element, would be a 2 to 3 ratio. E was right. And the same thing. So this is saying he knew that would have a charge of a +3. Also germanium he predicted. And look again, you can just see how well he predicted, all based on properties that he hadn't yet, he didn't know about, but he knew that it would be, or again, he predicted that it would someday be discovered. Okay, so the difference we're going to talk about. Mendeleev's periodic law can say what is going to be. And he can just say, based on properties, this is a prediction. Its density is going to increase. We should see the boiling points do this. The melting points will do this. They will all form compounds the same. But it didn't explain the why. So that's what we're spending this time, kind of the quantum is trying to predict and explain the why you see it. Why do we see these trends? And so if we know the why, that can help to predict the what as we're going at it. So what we're going to work on then is that taking those orbitals and giving a home or giving a location to all of the atoms within an electron. So remember, we write electron configuration. This is again just mathematical probability, and you're just kind of writing code. This code is going to be where the electrons are within that atom. So we know these orbitals exist. We talked about this. We looked at them yesterday. So we know we have S. K has 1 orbital. P's we looked at have 3. D's we know have 5. F's we had 7. Each orbital holds 2 electrons. Therefore, this has a total of 2 electrons. P's can hold a max of 6 electrons. D's 10 electrons. F hold a max of 14 electrons. So when you put them all together, you're giving an electron configuration. Know what this stands for. So if I have a 1s1, this is hydrogen. Hydrogen, you know, has a little electron. We're telling you where that electron is located. The number in front is not the period. It is the energy level. Many times energy level is on the same period, but it is not the period. It is the energy level. And remember, the smaller the number, closer to the nucleus, higher energy levels means they are further away. S is telling me what orbital. This 1 is telling me how many electrons are in there. So again, remember, we could do quantum numbers for all this. We won't be, but it's numbers, variables to put into an equation. there's some rules you have to follow. Pauli's rule says that there's a maximum of 2 electrons per orbital. That's one thing Pauli says. The other thing is talking about that when we start talking electrons being all negatives, one is going to spin clockwise, one has to spin counterclockwise. The way we will represent that is by the arrows. Up arrow can be a clockwise spin, down arrow a counterclockwise. We just know when we start putting them together that you are using opposite arrows to represent opposite spins. So that's the Pauli's exclusion. Only 2 per orbital. And again, it has to deal more specifically that they have to have unique quantum numbers. Mainly it's that they have to have different spins. Aufbau's principle says electrons are always going to go into the lowest energy orbital first. Typically they go in order. Then right here is where you get a blip. 4s happens before a 3d. And then it starts to get really kind of weird. At the higher energy levels you see a lot more changes, and you can't just fill all the first energy, all the second energy, all the third. It doesn't happen like that. But remember, we have a tool that we can use that will help us to fill it up. Huns Rule is saying that if there's more than one orbital, so we're talking about p's or d's, that if I have 3 orbitals, because again, they're all negative, they're going to want to occupy their own orbital before they would double back up. Because they're all negatively charged, they want to be as far away from they can from each other, minimizing the repulsion, so they do not start to double fill their orbitals until each orbital has an electron in it. So remember the periodic table. This is on page 11. You know this from the periodic table. So we call this the S block. Remember helium over here, so this is helium, should be in the S block. So when you go all the way through a block, that means it's full, so the maximum you'll put on any S would be a 2. Here's my P block, 1, 2, 3, 4, 5, 6. The max you put on a P block would be 6, because that's the maximum you can hold. D's, count, there's 10. Now follow the numbers. If you look, when you have lanthanum, which is element number, I'm looking at the periodic table on my iPad, number 56, if you look, 57 is down here. And there's some weird blips. I'm trying to remember what your periodic table, I'm sorry, but just follow the numbers. This is why I won't stop you on an F block. They won't stop you on an F block. There's some differences with the periodic tables where the lanthanide is. If you just follow the numbers, that's going to tell you how to fill it up. And we use it as a guide going through it. So let's kind of remind ourselves. For sodium, okay, sodium has 11 electrons. Sodium is right here. So you're always going to start at the top. So you say, okay, 1s2. You've gone all the way through it, it's full. Like reading a book. Start from the top and read it left to right. So then you go to the next energy level. And you have 2s, you're going all the way across it, so it's full. 2s2. So this is saying 2 electrons from the s orbital in the second energy level, 2 electrons from the s orbital in the first energy level. If you stopped here, that would be beryllium. Then what's the next thing you come to is the p block. So you would have 2p, and it's all the way filled, so you say 2p6, because that's the maximum in a p block. And then you have 3, and you're in the 3s, but we're stopping at sodium, so that means 3s1. Remember, you have double checks. If you add this up, it has to add up to the number of electrons. Adding this up means add up the superscripts. 2, 4, you have 6, so that's 10, plus 1 is 11. Sodium has 11 electrons. So find neon. Neon has 10 electrons. 1s2. Then you go to your next energy level. 2s2. 2p6. That would stop me at neon. That's what I want. Took care of your 6 electrons. Find lead. Okay, so lead is on 82. 82 electrons. Oh boy. 1s2. 2s2. 2p6. 3s2. 3p6. We stopped there, that would be argon, and we would be right here. Okay, this is where we have Huns Rule kind of takes over. Remember, you have a 4s, 2, but the D blocks are always one less than the period they are on. This is why the number in front is not period, because a third energy level is electrons in the fourth period, or excuse me, elements in the fourth period have electrons being filled in the third energy level, not just the fourth energy level. So D's are always one less than the period it is on. So you're going all the way through the 3D, so that would be 3D10. Then you have 4P6. Now we're on the fifth period, so it means it is a 5S2, 4D10, 5P6. Now we're on the sixth period, means 6S. Now this is where, look at the numbers. Now I know technically you would do a D1, then you're coming down through here, but you're going all the way through the F block, so you do not have to write 5D1, 4F14. You can do all the D's together, because that's where they're going to be. So I go through and just write my F's first. Okay, this is where you also have to be aware. The F's are 2 less than the period they are. Or you just remember there's only 2 F blocks, 4F and 5F. So you're going to go then through 4F14, then you come back into the 5D, 5D10, and then you have 6P, and you count, because we're going to lead right here, so it'd be 6P2. You guys probably had that done a long time before I did. Okay, there are a couple exceptions. In pre-AP, we didn't focus on the exceptions. You don't really have to focus on this. Good thing you don't have to memorize the exceptions, but being able to explain if it shows you an exception, that would probably be a good thing to happen. So some common exceptions are, and I'm going to show it on this, chromium is an exception, and copper. You would predict that chromium would have 4s2, and then you would have a 3d4. Well, what happens is if they can minimize, so look at what would happen here if you had a 4s2, 1, 2, 3, 4, 5, and you'd have a 3d4. So what happens by doing this electron is actually going to come over here. So now look at no orbitals are sharing, so there's less electron repulsion, so therefore this is just more stable. So it would be, why is this happening? It would be because there's less electron repulsion, because there are fewer orbitals being shared, so therefore it's greater stability. Greater stability is an awesome thing to be saying. It happens also here in copper. Copper should be, notice it should be that, 4s2, 3d9, and what happens is because a full shell is greater stability, that's why you actually, this isn't what happens, this is what you see happen. So if you ever see this configuration, it's not a mistake. So mainly that's the thing, is no, it's not a mistake. And why does it happen? Well, it must be lower energy, which means greater stability. Okay, you've seen me writing arrows. You need to know how to write arrows. Arrows are really useful in helping to explain things. So when we write the arrows, a box is for an orbital. You can use a line. I don't draw all my boxes. I do lines. Lines would also represent. The arrows represent the electrons. What you are doing is visualizing, and you're showing visually Huns Rule and Pauli's Rule. Now you have to label the orbitals because that's showing that you know Huns Rule. So the key thing is when you're filling up in electrons or orbitals, one in each block before you start doubling up. And this would be the configuration of 2, 4, 5, 6, 7. This is the configuration then of nitrogen. And then it starts to answer a lot of questions. It has 3 unshared pairs. This is why it forms a -3. it needs to gain 3 electrons to have that full orbital. So when we start explaining, orbital diagrams are really useful in being able to explain. These are types of questions that you could show. So I pulled this from an old multiple choice. So it says it's going to give you the configuration. So atoms, they have the electron configuration shown, the compound most likely to form with magnesium. Figure out what this element is. What ends in 3p3? Well, that must be phosphorus. We know that anything with a 3p3, it wants to have a -3 because it needs to gain 3 electrons to have that full valence shell configuration. So therefore, it's going to have a -3 charge. So magnesium is a +2. So to balance the charges, you know that you're going to need 3 magnesiums. You know any formula would be, 3 magnesiums. And they're calling it X, okay, X2. So you find your answer where you have a 3 to 2, your answer would be D. So to write the notation, you can use lines 1s2, 2s2. Okay, then we have a 2p. Now technically you should go 1 line each. This is how it would fill up. Then you start to double back up. Okay, if it's full, am I going to know if you did that? No. Just like in this, I know it's a 3p. I know it's full, so I'm just filling it up. Then we have a 4s. So each line is representing how many orbitals. The arrows are, there we go, the arrows are the electrons. So now we have a 3d. Hey, in iron, 1, 2, 3, 4, 5, 6 electrons. 1, 2, 3, 4, 5, 6 electrons. This is the orbital. You see orbital, that's arrows. Notation. Arsenic. So if you find arsenic, well, arsenic we know is going to be the same as this. Let's just do the shorthand. Let's do after argon. Let's just show the end of it. So we have 4s2. Then we know we're going to have 1, 2, 3, 4, 3d. We know it's going to be full. Then what do we know? We have a 4p. And in my 4p, you're going to have 1, 2, 3 electrons. So that's again showing Huns Rule. Doubling this back up shows Pauli's exclusion. The reason you have a 4s before a 3d is showing Aufbau's rule. Okay, remember the shorthands. So noble gases. This is group 18. What do they all have in common? All of group 18s. Yep, full orbitals, because I know you all answered me. They would have full orbitals. So we use this fact. We already wrote sodium. 1s2, 2s2, 2p6, 3s1. Well, this is the configuration of neon. So you're going to use that fact. So you take your element, go backwards. What's the last noble gas it went through? So this would be neon, and then you start after neon. Neon 3s1 then. So this is the shorthand configuration. Okay, what if they just give you a noble gas? Can we just say, yay, neon? Okay, cool, it's neon. Let's keep going. No, sorry. Go backwards to its last noble gas. That was helium. This really isn't that much of a shortcut, I'll agree. 2s2, 2p6. Lead. Remember that? It was a long one. So find lead, element 82. Go backwards. What was the last noble gas it went through? Xenon. So what you're saying is, okay, here is 54 electrons. Xenon is taking care of 54 electrons. I'm going to start at electron number 55, which is 6s2. Then remember, we have to go through the F's. Then we're going to come back through the D's. Then we go to 6p6. P2. Much shorter, but if you added it up, it would still be all 82 electrons, because here's 54, then there's what, 56. 56 is 64, so that's 70, and then there's 82. So there's all 82 electrons are still taken care of. Valence electrons. Last thing, remember these are outer shell electrons. Shell, or your highest energy electrons. Okay, when we can write their configurations, we're looking at the last, electrons really after the noble gas. So you're looking at the last S and P electrons. So for sodium, after its noble gas, we know everything in group 1, remember, has one valence. Its one valence electron is 3s1. Compared to, let's say, barium, we know it has 2. Which 2, it would be the 6s2 electrons. Aluminum has 3. It has 3 valence electrons. They are the 3s2 and the 3p1. There's your 3 electrons. It's going to go to sulfur. Has 6. What 6 are they? They're going to be the 3s2, 3p4. There's your 6 electrons. Xenon. Xenon has 1, 2, 3, 4, that's 5. 5s2, 5p6, showing you its 8 valence electrons. So you have on the next page some practice. You're going to work on that, and then after that there is an activity that you need to work on. So homework is to finish the page 12 and to finish the activity. So you can kind of decide, you want to work in small groups on your activity. It's computer activity, and use the computer here and save page 12 for homework. Might be a good idea and a good thing to do. I will see you next week. If this is A day, I will see you or on Tuesday or Wednesday, just depending what day.